So welcome everyone to the talk Multi-Service Reactive Streams using Spring, Reactor, and RSocket. It is quite the mouthful. I assume most of you heard the keynote earlier today where Stefan and Steve, the two French Stefans, talked about RSocket, and maybe you even went to Stefan's earlier talk with Rylan from Netify talking about RSocket. So we're going to take a little bit of a different tack. We've talked, sort of at a high level. We've seen them, demonstrate a bunch of use cases in the other talk. But this one's really going to be a deep dive into the protocol and why we think the protocol is such a great thing. What are the features of it? What makes it really, really well suited to modern network communication? Before we get started, my name is Ben Hale. My official day job is I am the lead of the Cloud Foundry Java experience, which sort of puts me in this intersection of my long history working for the Spring team and more recently observing how Spring users like you run applications in the cloud, the problems that you have, the solutions you're trying to solve. And so it's put me at a really, really good place in order to sort of watch as things like raw REST with things like Netflix OSS wrapped around it are reaching the limits of what they can do. And so this is why I'm really, really interested in RSocket. Rawson?
My name is Rawson, and I'm a committer on the Spring framework. I am involved in anything web-related within the Spring framework, which includes the new WebFlux framework we have and all the reactive efforts surrounding that. Also the messaging, the WebSocket and Stomp support that we have in the Spring framework. And related to that, as we build out a reactive stack, we also look at the messaging side of things and for solutions. And RSocket is something that we're really excited about, and we're hoping to bring support for that, possibly in the Spring framework, maybe next to Spring messaging, but it's something that we're still figuring out. The RSocket Java project is something that Ben has been involved in, so he actually knows what he's talking about, so he's going to be on stage here much more than me. And then I will come up for a short period to show some of the stuff that we're experimenting with and thinking about putting in the Spring framework, and we'll be very interested to hear feedback or anything specific that you're interested in.
Great. Thanks, Rawson. So let's go ahead and kick things off. So how many people in this room today already do reactive programming, or what you think reactive programming is? OK, so certainly not everybody. The Reactor team over here is heckling me. Do you actually do reactive programming, or do you program reactive? That's the real question. OK, so just as a quick refresher and give everybody a nice level set, in general, we view reactive programming as the next frontier in Java for high-efficiency applications. So you're going to see a lot of stuff, a lot of the time that the Spring team talks about reactive. We talk about it in this idea that it is more complex to take on, but the rewards for taking on that complexity can be very, very high. And where that trade-off really, really matters is in applications that need to be really, really efficient. And by efficient, what we're effectively saying is, all of us have experienced at some point an application that has almost no CPU usage, and yet every single one of its connections have been occupied, right? Because you make some outbound connection to a database, you make some outbound connection to another microservice, and stuff just starts blocking. And so maybe you take Tomcat's default from 200 threads to 500 threads, and you still end up with it. And you're like, I'm paying for these AIs, or I'm paying for this VM on AWS, and I've got like 10% CPU usage and 5% memory usage, but I'm running out of connections. You start going towards 2,000 connections, 2,000 threads, and you realize all of a sudden your thread stacks are worth 2 gigs of memory, and this doesn't seem to be the appropriate way to do it. And so reactive really plays really nicely in here, because it's a way for us to say what we actually want to do is break this thread per connection model, which is the primary problem that we see here, and go to a non-blocking model. This is the key, right? This idea that what I don't want to do is ever hold on to resources. I don't ever want to hold on to a thread when I'm not actually using it. So We often see, especially when we're talking about reactive programming, that it's fundamentally non-blocking, but it is often paired with asynchronous behaviors. We're in this room today to talk about a network protocol, and so obviously this is a great candidate. Reactive itself doesn't have any particular opinions on async. If you take a look inside the implementations, sort of thread decisions are kept very discreetly off to the side. If you've ever written any reactive code that doesn't make a network call, it probably all ran completely synchronously, because it is the most efficient way to run reactive code. Anytime you have to jump a thread boundary, there are implications of that. But the key differentiator I want you to take away from async versus reactive is this idea that there is this thing called backpressure, right? And so we often refer to it as reactive backpressure, reactive streams backpressure. A good way of thinking about this is that it's actually pull-push backpressure. A key tenet of the reactive stream specification is this idea that a publisher cannot send data to a subscriber or to a consumer until that consumer has indicated it is ready. And the way it does this indication is after the entire subscription is ready to go, it says, I request N number of things. I request 8 items to come down, or I request 16 items, or I request 1,024 items to be sent to me. If you have less to send me, or fewer to send me, I should say, then send me those fewer and tell me you're done. If you have more to send me, well, you only get to send me this little bit, and once I am ready, I will request that you send me the rest of them. You don't get to overflow my incoming buffers, but it also has an advantage not just for the subscriber, it has a huge advantage for the publisher. Because it means now that the publisher has an indication of when it needs to materialize data. So I did a talk in the session previous to this about R2DBC, our reactive database driver. And so it's a really good analog to think about that. Imagine if when you queried 100 million rows from your database, rather than it basically spinning up all 100 million rows off of the hard drive and sending it across your network connection, coming over to the other side, maybe the other side, the heap explodes and your entire VM goes down because you requested more data. Maybe in a better scenario, it has TCP backpressure, and so it doesn't blow up that VM, but you've still got your database now that's basically holding on to all of this stuff in memory. It has had to materialize, do this really expensive thing, and now sits idle, just sort of about to explode with all this data. Part of the pull-push backpressure, in addition to guaranteeing that the subscriber is never overflowed, is it means now that same database might say, oh, I only need to materialize the next 8 rows. I only need to get this small bit of data off the hard drive. I can do that really quick. I can bring it up and throw it off. And once you're ready for more, I'll go back to the hard drives and get the next bit of it. So that pull-push backpressure is the key thing we talk about when we start talking about reactive programming. So I used this example as well before. We know that reactive programming works quite nicely, especially around network communication. And so this is an example of a Spring Webflux controller method. It's a get method, and all it basically does is makes 2 different network calls using our reactive-based web client. Calls the alpha service for its health, calls the Bravo service for its health, builds some sort of composite and returns those. And if we remember from the talk earlier today in the keynote, it means that nobody's waiting around, right? So when the web client fires off this GET request, it immediately gets off the thread, and another thing can use that thread if it wants to, while it waits around for the service on the other end to come back and respond to it. So this is great generally, right? Like we have optimized effectively this JVM that we're operating in to be as efficient as we can make it to be. But there are still some barriers to using Reactive Everywhere. I say Reactive Everywhere with an asterisk. I'm a true believer, right? I don't write code that isn't reactive anymore, but that's not something you should do, right? Like maybe you get to where I am one day, maybe you get to where the Reactor team is one day, but it is much more pragmatic and much more appropriate for teams to selectively pick places where going with a reactive programming model has immediate value and immediate improvements in performance and efficiency in your application. So instead of saying reactive everywhere, maybe we say reactive everywhere that's appropriate. And we talked in that previous session, data access is one of those places where even if I knew I had a use case that would absolutely benefit from doing reactive programming, if I needed to go to a database, I couldn't. Right? So we have a project that attempts to solve some of that problem, because JDBC is totally blocking, and you can't convert blocking to reactive, just as a first principle. But we also see that another place that's sort of kills us a bit is this idea of cross-process backpressure, basically backpressure over a network. Like, I can guarantee that I never call for more data than I can handle inside of a process, but what happens when I have to make a call to another microservice in my microservice mesh? How do I guarantee that it doesn't materialize a whole bunch of data and it doesn't attempt to send me all of that data? Imagine a JSON payload that had 10 million elements in it, right? Like, you could imagine this being a very large problem from a heap perspective. And so, RSocket. Unlike the slide today, this is actually centered this time. It really irritated me on the main stage that it wasn't in the center. OK, RSocket. RSocket is this great protocol that was, sort of initially conceived at a number of high, how do you say this, high scale, global scale internet companies in the Bay Area to solve these kinds of problems. Because what they were finding was that HTTP just didn't cut it, right? Like, they did actually need to communicate this idea of reactive backpressure across a network. So RSocket is, in a very wordy expression here, a bidirectional multiplexed message-based binary protocol based on Reactive Streams backpressure. We're going to talk about every single one of those things in a moment. As we saw in the slides today, it provides out-of-the-box support for 4 very common interaction models, and including a bucket channel there at the end that basically allows you to implement any other programming model you might want to take a look at. Oh, I should absolutely say, since this is going to be a really deep dive into the protocol, if there are things that I gloss over, you don't quite understand, I haven't explained how reactive works or something to your liking, go ahead and just raise a hand, let me know. If we can answer it quickly, I'd prefer to do it sort of in line to make sure everybody gets a little more knowledge. So, first things first, it is a message-driven binary protocol. So, we have this idea that given a network connection, a requester and responder interaction is broken down into a discrete set of frames. So you'll often hear something like this referred to as a framing protocol. Each one of these frames encapsulates a message of some kind. And this is probably a little bit different than when you sort of think about how something like JMS or RabbitMQ works, in that those seem to have, like, here's an endpoint, here's a source, or vice versa, and you are trying to send a discrete message. Here's a JSON payload or whatever it needs to be, something serialized. I want you to send it over there, and then it's eventually going to get forwarded to a bunch of listeners over there, right? Like, that's how we sort of think about message-based. But message-based can be so much richer than that. The payloads, right, the data that actually needs to be transferred across, is one kind of possible message. And given sort of knowledge, given a bit more structure around a protocol, you could say that these messages are also like, how do you set up this? How do you guarantee that both ends are going to do content negotiation? They realize it's JSON payloads or protobufs that are going across the wire. How do you instantiate and say, or how do you initiate a certain kind of request? I want a request for a stream of things to come back. I want a request for a single response to come back. All of these are messages as well. And that's really, really key, because what we want is each one of these things to be discrete messages so that we can talk about a really good feature a little bit later. The framing itself is binary, which means it is not human readable. And this is, like, especially for people who have done REST development their entire lives, which was me, basically, up until RSocket came into my life. The ability to just hook Wireshark in or something like that and actually be able to read what's going by on the wire is really, really useful. But it turns out that the penalty for doing that is so large when it comes to machines actually decoding this thing that it's totally not worth it. Right? If you take a look, HTTP2 is a binary protocol. It is fundamentally sort of the same interaction model that HTTP was, but one of the big changes was it became binary protocol, right? All of the framing and sort of infrastructure about how a request is structured and sent and responded, everything but the payloads, basically, it collapse down into a binary protocol. And this leads to massive efficiencies. Turns out that string parsing is basically the worst possible thing in all of computer science. You don't want to do it. This is great. As much as we as developers love looking onto HTTP streams and seeing something human readable and being able to diagnose it, it is so much rarer than the production case of everything is just working fine. And so that penalty is absolutely worth paying for us as developers and can be easily solved with tooling, putting something into, like a plugin into Wireshark that knows how to decode these things. The key takeaway from this is, as I have said, that it is a message-driven binary protocol that does not make any judgments about the payloads you want to send across this protocol. It's basically just a bag of bits, right? And if that means that you've got a bunch of JSON ASCII characters or UTF-8 characters that are translated into those, and you have some sort of, like Wireshark or something that can inspect it, it will turn them right back into ASCII characters for you at the other end. We're only talking about the framing around the payloads themselves. You aren't restricted in what you can send to binary. And here is the key, the key reason we want our protocol to be message-based, and that is so that we can multiplex on a single connection. So we have learned from the HTTP1 days, I suspect looking around that there are a number of you who don't remember the HTTP1 days, connections that are only used for a single request are massively inefficient. Especially you start taking a look at web browsers, you realize it was not feasible to open a single connection for every resource on a page. And so now in HTTP 1.1, they introduced this idea of pipelining. I can send 7 requests in a row, and I know that the responses that come back from that are going to be 7 in exactly the same order they went in. Huge problems with this. Proxies don't support it. You end up with head-of-line blocking, which basically means the first request I sent in was this biggest thing. I needed to download this giant image or something like that. And the 6 that followed behind that where I need 1K of HTML to render, or JavaScript to render on this page. And so everybody waited for the thing that came in at the top of the line, or at the head of the line. And so you saw browsers trying to get around this and basically say, OK, maybe I can intelligently figure out which is the one that should go at the end of the line and which should go at the beginning of the line. And it was just a disaster, right? Like pipelining doesn't really work, and no one really takes advantage of it because of that. And again, HTTP2 sees this same problem, and HTTP2, like RSocket, is a multiplexed protocol as well. Multiplexing basically means that there is a single connection, and every message that goes across that connection has a logical stream ID. In fact, in the implementation details, there are some times where we have a stream ID. But what you want to do is sort of think of this as a logical stream. You've got a big pipe, and inside of that pipe, you can send a bunch of stuff on. This runway, this runway, this runway, this runway, this runway. And as the messages, sort of follow one another, but they can be decoded on the other end, broken out into logical interactions, regardless of the physical connection, the physical socket connection between those two. We also now have a protocol here that is bidirectional. So many protocols, but notably not TCP. And this is from the Vint Cerf looking angry slide earlier this morning, have a distinction between the client and the server for the lifetime of a connection. HTTP, again, since it's something we recognize, is one of these kinds of protocols. A client can make a request to a server cannot make a request to the client. The division means that one side of the connection is responsible for all levels of initiation, and the other side must initiate all levels of responses, or all other responses that are going to happen. Even more flexible protocols like HTTP2, which do purport to have this bidirectional kind of communication, aren't actually fully bidirectional. So for example, a server can't sort of, as soon as a connection is made, initiate a connection to say, hey, client, go send me a whole bunch of data, without some access by the client for saying, I am ready to listen to what you're about to say. So one of the key principles, again, inside of RSocket is this idea that once a client initiates a connection to a server, so someone has to be responsible for saying, I want to connect to you, and someone has to be responsible for saying, I am listening for connections. But once that handshake is done, both parties in the connection become equivalent to one another. Both parties can initiate a request without any knowledge from the receiver, whether it's going what was previously client to server or what was previously server to client. Either one of them can interact as a full-fledged party, asking for information and getting responses back from one another. And this is actually like, I want to say this is revolutionary, except it was revolutionary 40 years ago, and we sort of lost it, right? We went to arguably simpler protocols that were serving one particular goal. I want to request you send me, I believe the emoji was a newspaper this morning, right? You just send me a newspaper, which I think is a good analogy probably for this kind of protocol. So the final big feature is that, I think this is the final slide here. The final big feature is Reactive Streams backpressure. So everything I described to you, that I want it to be message-driven, that I want it to be binary, that I want it to be multiplex, that I want it to be bidirectional, could be implemented in a protocol that doesn't have anything to do with being reactive. But the key thing that this protocol then builds on top of all of this, right? Like basically we've talked about TCP primarily right up until this slide, is this idea that we know that reactive backpressure, this pull-push backpressure, has advantages to both the requester and the responder, but we need to then find some way to communicate that information across that network link. So network protocols generally send a single request, receive an arbitrarily large response, nothing to stop that responder from actually overflowing us. In most cases, since most modern protocols are based on TCP, we do have some safety. TCP backpressure can throttle the responder. Basically, the either queues on networking devices that are inside of a stream, or the client itself can basically say, it won't act a packet coming from TCP. Won't say, I am ready for, at this very, very, very low level, for you to send me more data. But it does not actually solve the responder problem, where there's a lot of data being queued up out of the other side that needs to still be sent on, especially in poorly written applications. And it also doesn't really, it's very difficult to reason about as an application developer, right? If I tell you that my TCP buffer size is 8K, right, and your responsibility is to go off and I need to pull 100,000 users, how many users do you buffer in 8K? What does that mean? Like, do I need to go and request from the other end, like 8K times, I need 150 users, and I need to figure out what that is, and then figure out how big a user is, and all that kind of thing? Is that something you can reliably reason about as an application developer, as someone who's moved up the stack and doesn't really think about TCP? And the answer is no. And so it's really difficult to like tune TCP buffer sizes and MTUs and things like that, because what you as an application developer actually care about is, I need 150 users, 150 customers. And so I want to request in a progressive form, or a progressive fashion, I want you to send me 150 customers. And so the protocol accepts that it is an application level concern to decide how many things get sent to it. And then, as we said earlier, Reactive Streams backpressure ensures that data is only materialized and transferred when the receiver is ready to process it in standard Reactive Streams fashion. So any questions on sort of that first tranche of, here is what this protocol is? No? OK, good. Yeah? So the question is a responder required to sort of say how, or sorry, is a requester required to say, I want this number of things, right? And the answer is twofold. At the sort of Reactive Streams spec layer, the spec itself says you can request long.max, and long.max means infinite demand. Send me everything you can possibly send me as quickly as you can, and then when you're done. Kind of thing. And so this is really useful inside of a JVM, where you're just trying to flush data through in a synchronous fashion. The RSocket spec, actually, this is, I said it is completely RSocket compatible. This is actually the one place it diverges from the Reactive Stream specification. Because we're dealing with networks, asking for everything means you probably don't actually understand what everything is. And so I think its limit is like int.max instead of long.max. There is no send me everything you could possibly send me. But it doesn't really matter, because no one should really be making that request for even int.max. You're asking for typically for significantly smaller numbers of things. So like in 16s or 32s or 128s or 1024s, because you still have to process them on the other side. Maybe you know you're going to be running on super beefy hardware, and you bump that to, I want 5,000 things at a time. But you don't really want to ask for unlimited, because you don't actually mean it most of the time, especially when you're going across the network.
I can't agree with that. I always want all of the prices of Microsoft streamed to my client.
As an application right. So the comment was, I actually want all of my customers. And the subtlety that I did not actually demonstrate here is that an application developer never chooses how many they want sent in the first place. It's the framework below it. The client actually says, I want you to send me a flux. I want you to send me a stream of all of my customers. And below that, the framework, whether it's RSocket or Project Reactor, is responsible for saying, I want 16, I've processed 16, I want another 16, I will process another 16. And that is completely invisible and transparent to the client itself, who gets all of them. Yeah, cool, no problem. That was me not being clear. It's absolutely fine. Any other quick questions? One back there. Yeah, so the question is, what can an RSocket client actually communicate to, right? Does it have to be RSocket on the other end? And it does absolutely have to be RSocket on the other end, right? This is not HTTP. If you don't know how to form these frames into a thing that can be sent, then you're not going to respond appropriately. But we're going to talk a little bit later about it. There's no reason you can't integrate this into basically any application that's out there. The standard itself is not language specific. It's not Java. It's not COBOL. It's not JavaScript. And so you can just sort of plug this thing in to your server and say, hey, you know, I'm an old COBOL server. I can respond as long as I know what the interaction model is supposed to be. Like, COBOL doesn't exist, but in theory, you could do such a thing. OK, so let's take a look at the interaction models now. So the first interaction model is the request-response interaction model. And it's actually never listed this way. It's never the first one in the spec. It's never the first one on anybody's slide. But I want it to be the first one on my slide, because it's the easiest one to reason about, right? This is what everybody knows. Standard request-response, HTTP-style semantics. And one of the really interesting things is we're giving you this really, really advanced protocol. It has all of these kinds of things. And the very first thing we do, and expect to be the dominant interaction model for a long, long time to come, is going to be the same request-response, single request, single response model that you've seen. In this particular case, this is an immediate improvement over certainly HTTP 1, because those request responses are completely asynchronous. They have some kind of demand, so they're sort of lazily initiated. And they're multiplexed over that network, so you can more efficiently use resources. And so an example of something like this might be, I've got my app on my phone to my bank. It sends a request of the account number, and it responds to my negative account balance, right? And so you'll see an API that looks a lot like this. I have my client. I initiate a request response passing in this payload, and it is going to give me a mono. And so we've talked a lot about the Reactive Streams API. And the Reactive Streams API declares this thing called a publisher. And a publisher has 0 to n responses from it. And it's the only type there is. But you'll always see when we start talking about this kind of thing at a conference like Spring 1, we really start talking about Project Reactor. It's not the only Reactive Streams implementation, but obviously it's one that's near and dear to our heart. And very specifically, it has split publisher into two types, effectively. There is a flux, which means 0 to n, sort of exactly publisher semantics. But we also have a more constrained type called a mono that means 0 or 1 responses. So in this case, we know that when I request something, if I only expect a single response back, semantically, it's something that we call a mono. You know you're only going to get 0 or 1 of these. So a variation on request response, the one that does normally come first, is this idea of fire and forget. So in this particular case, we want to optimize for the case, which it turns out to be super common, especially in mobile development or mobile applications, that some client needs to send a request back to me, basically give me a bunch of data or give me a piece of data, and I don't care if you got it. If you lose it in transit, if there's no sort of durability or guaranteed delivery or anything like that, but who cares? There's huge amounts of data in the world. I mean, the existence of UDP proves this, right? That we're just going to send it, best effort, good enough for me kind of thing. Huge, significant efficiencies if you don't have to keep connections open, both on the network side, like you don't have to act back that you have received this thing successfully. Client and server processing can basically short circuit immediately. They don't have to finish off any sort of data transmission handshake between, and they can release resources like connections immediately. And so, as we say, non-critical event logging is a really, really common thing when it comes to this. I just need to send a bunch of logs to you, right? Or like, we have a live connection right here, and I just want to send back some things about like where this person's typing. Or one of the most compelling use cases I've ever heard about this is someone on a support call, right? There's something wrong with my phone, with this application on my phone. Okay, what's your UUID? Type that in, and we can just sort of send a message over to the cell phone that says, okay, start streaming logs. Like, I don't want my entire footprint always sending me logs from every single cell phone in the world, but I can hook into your phone, tell it to start sending me some of these event logs, and it just starts sending them to me, right? That I don't get some of them, that's fine, right? We're just doing some diagnostics on a phone or something like that, or over a Skype or something. And so the fact that data doesn't come back reliably is no big deal. RequestStream. RequestStream, I think, is really interesting because it's the first one that sort of stands apart from the request response that we're all used to with HTTP. So actually, one final thing. You'll notice the response type is mono again, but a mono void. Because the void type cannot be instantiated in the JVM, mono void is a shorthand, well, a longhand way of saying always going to be 0. So if mono is 0 or 1, but you can never instantiate the 1, mono void means 0. So Fireandforget never has any response. It just says, I'm done, I'm complete. So back to RequestStream. So this is analogous to request response, but we're basically asking for a collection of data where that collection may still be 0 or 1 or n to be streamed back to me based on a single interaction, right? And so if we take a look at the signature this time around, we don't see a mono. We see a flux this time of whatever that payload is. This is basically saying, now, once this response has happened, I can listen to it. And for every single element that comes through here, I'm going to handle each one of those things persistently. So imagine you have done an HTTP query for a list of things, a list of those 150 users, right? Those always come back in one giant payload, right? One giant JSON payload is going to get streamed to you. Maybe you're super sophisticated and you do paging instead. Now you have to do a request for a small group, and then another request for a small group, and then another request for a small group. What this aims to do is instead say, I get to make that one request. I don't have to do all of these paginated multiple network requests to do this thing, even in the case where you're pooling connections and things, making the round trip of request response ends up becoming expensive. But what's going to happen is I say, OK, send me those 150 users. But then on my side, it is still my responsibility to say, OK, now send me the first 8. And then you over there materialize the first 8, and they come to me. And then I say, send me the next 8. And then eventually you get to 48, and then I ask for the 7th batch. And there's only 2 more in. So then it sends me 2 more, and then it sends what's called an on-complete signal saying, I have sent you all that I have. You have requested whatever you could handle, but I'm done sending them. You don't have to listen anymore. And that sort of falls through the reactive flow. So a great example of something like this might be, I can't imagine you're really using your account application, your bank application this way. So the analogy kind of strains here. But imagine you're looking at your account right now, right? It has all of your current transactions, and your partner next to you just goes and swipes the card for dinner. It can show up instantly because you've said, give me a stream of all of my transactions. And the first thing it did was went and grabbed every single transaction in your bank account all the way back to the beginning of time, put them to you. You've displayed in the UI, and as a new one comes up, you've said, I'm still waiting for another 8 one of these, and another one comes in. And then they go over and they buy a shirt over at the gift shop in the restaurant, and then another one shows up kind of thing. And that's what a stream aims to do, is not only is it a way to efficiently get a collection of data, it also potentially leaves open that request to fulfill more data as time goes on. And this opens up, now all of a sudden you're like, request response, yeah, we can do that with HTTP. Request Fireandforget, we can do that, maybe not as efficiently. But this idea that this thing stays open based on a single request is really, really powerful. And using request end semantics underneath it, this pull, push, back pressure, means that it's done in a very efficient way that doesn't penalize either the publisher or the subscriber. Finally, the 4th interaction model is called a channel. And a channel, as you can see, takes a stream of payloads going in and a stream of payloads going out. And that's basically completely unstructured when you see something like this. It's just a bidirectional stream where you can send any data you want in one direction, you can send any data you want in the other direction, and you are responsible for coordinating what those mean, and if messages get crossed up and things like that. So it allows arbitrary interaction models. And if you take a look at this, you can instantly see exactly how you would implement the other three interaction models using this kind of thing. And so I don't believe we actually implement it that way, but you can see how logically they are all sort of refinements of just straight flux. So some examples around this, you're requesting an initial burst of state. So I request with my account number, and you respond to me with a real-time stream of transactions. But while that connection is open, I say, oh, there's too much stuff here, right? Like I don't want all of my T-shirt purchases or all my gift shop purchases. So I say, eliminate everything that says I bought a T-shirt. And immediately that goes, and the subscription on the other end is updated instantly, effectively. And now the stream of data, which has not been interrupted, you're still listening to the same flux of data coming in the other direction, doesn't send you quite as much stuff as it did before, right? And so this allows you to do these really complex, I have a persistent connection that will exist the entire time my application on the phone is open, and I can just do everything across it. I can send messages that are understandable by one side, understandable by the other side, and I don't even have to necessarily initiate all of these request response or request streams if I don't want to. There are reasons from sort of logical division of code that you want them to be discrete, but there's nothing to stop you from getting this, I just have a pipe that messages go across kind of behavior. So before we jump into some code, any questions? Sure. This kind of implies a stateful server. Not necessarily. Like connections can stay open, but imagine that this is backed by a database, right? It may still listen to a thing that says, okay, this person needs for account 100, right? And so it forwards that request on. Imagine we don't have R2DBC, so all 1,000 records come into memory, and it just sends those on. And again, in the same way that the client doesn't realize that it's being partitioned and using request end under the hood, the producer, the publisher, doesn't know that either. It basically says, and here's a collection of 150 users that need to get sent. The fact that they sort of go off at 8 interval, or groups of 8, windows of 8, it's completely unaware of that. So it's maintaining state for the duration of the request, but that's sort of no different than a stateless server already does today with HTTP, right? If it takes 2 seconds to get the data sent across, even in like a stateless microservice today, there is some state, right, for the length of the request and the time it takes to respond. And so it's the same kind of thing. Yeah. The channel model, yeah, you could absolutely. But I mean, it sort of has the same semantics that there is state for the length of this request. And the fact that we don't have, the request stays open forever, and a message comes in that says, okay, I need all of these account things, and I hand those back. Once it's done handing those back, the state is gone, right? Like it has taken it out of the database, sent it across the wire, and it's been garbage collected. That it's listening for another message to come through isn't really state maintenance in the classic sense of thinking about it. But there's no reason it can't be. The channel is a great way, any of this, like, can be plugged in on top of a stateful server as well. If you want to have something where you are keeping some sort of persistent data, that each message that comes in from the client along the channel modifies a continuous query you've got to the database or to whatever your NoSQL data store is, yeah, maybe there is some state modified or state held, what the current continuous query is. And this comes in and it modifies it and restarts whatever that query is against the database, or modifies the query against the database and new data flows through. Sure, you can maintain state there if you want to, but there's nothing about the protocol that necessarily implies state maintenance, even in the channel case. Great question. Wow, okay, so that started a lot of other questions. Hold that question. Hold that question. There are slides about this. There are demos about this. One more in the back. Yeah, so the question is, what happens if I've got this long-running persistent connection from one end to the other and one end crashes? And the answer is, at its base level, you have two sockets connected to one another communicating, as exactly the same as if you had an HTTP connection open with keep alive, right? Just because there's no active request response happening, it's alive. If one of those ends, the underlying level 1, 2, I can't remember what level it is, something like TCP, like send some ACKs, send some OKs, send some closes, and like things die, right? Like, and there's nothing gonna stop those kind of semantics. If a connection is dead, a connection is dead. We will talk about a feature at the end to deal with that RSocket provides that says, if something fails, like if this connection dies for any reason, server dies, I switch from a cell network onto Wi-Fi, anything that breaks a socket connection, you can probably do something a little bit better. And so we'll talk about that as well. Good. One over here.
Any of these interaction models has a higher probability to lose messages?
Do any of these interaction models have a higher chance of losing messages? The only one that has any chance of losing messages is request, fire, and forget, right? Because you're going to fire something over, and while it's in the air between your phone and a cell tower, the apocalypse happens or something like that, right? And the message doesn't get there. The client and the server were not sort of keeping track of those messages being sent, and so it's just disappeared into oblivion. All the rest of them, when we talk a little bit later about how we do disaster recovery in RSocket, there can be a record to guarantee durable, reliable delivery, if you want to. So let's take a look at the RSocket API. And I was talking to one of the core Reactor team members earlier today, and her demo went absolutely horrifically today. So let's hope the gods are smiling on me and she has taken all of the bad karma. Okay, so I said a little bit earlier that these are what these APIs would look like, for example. No, this is exactly what those APIs actually look like. So this is the Java implementation of the RSocket interface. It's got some stuff that it touches, but you'll notice there is a Fireandforget, there is a request response, there is a RequestStream, and there is a request channel. So you'll see in all return types, we strongly type them to Flux and Mono, basically Reactor types. Anything that's an input, specifically around request channel, ends up being a publisher. There are interesting reasons involving the Java type system and inheritance why this is true. But suffice to say, you are seeing the exact same signatures that we published a little bit earlier. And so if you wanted to use this library, so there is an RSocket Java library. If you go to RSocket.io and follow to code, you eventually end up in GitHub, and you can download this library and use it. So what does using it look like? So let's think about what the server side looks like. So let's ignore this bit in the main method here. So the most traditional way to implement an RSocket interaction is to extend this abstract RSocket sort of adapter layer. You could implement the RSocket interface directly if you wanted to. This doesn't do anything other than put a bunch of unsupported operation exceptions into the interface so that you can implement it a little bit easier. You only need to do one method at any given time. And I realize now, being a reactive programmer, I have made my code very, very dense, which may scare the hell out of a lot of people. That style is not for everyone, certainly. But you'll notice that I am implementing the RequestStream interface. A payload is going to come into me, and I need to return a stream of payloads. And for this implementation, this default simple service, what the goal is you are going to send me a payload that has an integer in it. And inside of that integer, it is going to what do I want it to do? You're going to tell me how many messages you want me to send back. So you send me 1, I send you 1 message. You send me 10, I send you 10 messages back. And so effectively, what we're seeing here is given the payload, so this hunk of code right here, given the payload, and I'm going to parse it out and say, OK, it came across as a string, so I want to turn it back into an integer. First thing I'm going to do is say that I just received this particular integer. You just asked me for 10 messages. And then I'm going to do this flat map many. And this is effectively a way of saying, given this I, given this number that is flowing through this reactive stream, I want you to generate more numbers. I want you to transform that or flat map it from a single stream into a bunch of things, right? From a single thing into a bunch of things. And so in this case, we use the flux.range operator that says, I'm going to create a bunch of numbers between 0 and the number that you gave it to me. We'll log out exactly what we're sending, and we're going to create that payload. So we have an implementation of how we would handle this. And one of the key things to sort of keep in mind here is this is a super trivial implementation. It effectively means that my application is only expecting ever a single request stream to come in, right? Like it's the only payload that could ever be a request stream. More complex applications where a bunch of different operations might need a stream of things mean you then have to inspect the incoming payload, find out what it actually meant to do, and then route it to code that knows exactly what it needs to do. So it can get a bit more complicated when you're doing something like this. So what we do with that is we start an RSocket Factory and say this is an RSocket Factory where we want to start receiving messages. We are the server side in this thing. And remember, as I said earlier, once client connects to server, the distinction disappears. The thing that's going to accept connections is one of these default simple services. It knows how to handle incoming requests. And this is one of the things that was asked a little bit earlier. What transport exactly is this using? Excuse me. In this case, we're going to use the TCP server transport. We're basically going to route this communication over raw TCP. We're going to write bytes onto a TCP connection without any HTTP framing, without any HTTP2 framing, or anything like that, just bytes on TCP. We go ahead and start it up and wait around for it to run. What do I actually want to run? Raw, nope, raw server. That'll do it. For a second to compile this whole thing. Oh, God. OK, good. It all worked last night at 2 a.m. OK, so now let's take a look at what a client for something like this looks like. A client for something like this, one of the key design goals of this RSocket project. We pull up RSocket again. Have I lost it? RSocket. There we go. One of the key design goals of the RSocket project itself is that we want both the client and server to be symmetrical. So before, we implemented this interface. We said, what I want to do is when a request stream comes in, it calls this implementation of the interface, it calls this particular request stream method. But at the other end, as a client, we want it to be symmetrical, meaning that from the client's perspective, they feel like they're actually calling that exact same method. They don't realize that, like you could see a test implementation or something where the implementation of the RSocket interface that was being called by the client is actually the exact same instance inside of your JVM. And the fact that it has then been separated via a network transport like TCP is sort of hidden from the process. And so if we take a look at the client, we see that is what happens here. We'll come back to the startup in a second. But effectively, we're going to say, OK, for the numbers 0 to 10, we're going to send individual messages. We're going to say, I want you to send 1 and get some responses back. And I'm going to send 2, and I want to get some responses back. And I'm going to send 3, and I'm going to get some responses back. We wrap that up in a payload, and we call RSocket RequestStream. We have one of those RSocket things. The fact that it happens to go across TCP versus being local or going across HTTP or something like that is completely abstracted from the client itself. Obviously, as we have all learned in remoting over the last 2 decades and 3 decades and 4 decades, this does not absolve you as an application developer of knowing that you are going to go over a network link and all of the implications about reliability and performance and speed and latency that are implied there. But from a programming model point of view, this is actually abstracted. This time, we're going to use the RSocket Factory to connect out to something rather than to receive incoming connections. We say on the client side, we also want to use TCP this time around, and we start it and wait around for some results. And so if everything goes properly, we'll take a look at the server side here. The server side first has received 0. then didn't send any, received 1, so it went off and sent 1, it received 2, it went off and sent 2, and behaved exactly the way you'd have expected it to behave. On the client side, we have the same thing where it went off. One of the really interesting things is because of the way non-blocking works and how fast it can possibly be, all of the outbound messages were sent before the very first message managed to get back on the thread. The messages may have even been sort of sent across the network, but because we try and do some aggressive optimizations to stick on the same thread for as long as we possibly can, because thread context switches are expensive. Instead, we're just going to get them all out the door, and then they're all going to come back, and a better demo writer than I would have put better indicators on here. These did all come back in the correct order that they were supposed to for the requests that they went out for, but they're interleaved in response, again, because of this asynchronous non-blocking behavior. So that's sort of the raw RSocket API style of programming. But RSocket is, as you saw, there was, Steve showed a slide that had sort of RSocket in blue, had a bunch of transports, and it had a bunch of payload types, and had a bunch of programming models and things like that sitting on top of it. In fact, programming model before payload type. RSocket, and one of the things that has always really attracted me, like a moth to a flame about RSocket, is that it is amazingly flexible. It took a look at things like HTTP and gRPC and said, you guys are inflexible, and you're not even inflexible in good ways, right? Like you've instituted sort of arbitrary limitations around things that we don't think you should do. Language agnostic, first off for RSocket, this is not sort of novel. There are implementations today in Java, JavaScript, and C++. You can thank Facebook for the C++ one. But Kotlin, Python, there are prototypes in other languages as well. And the protocol is, I have spent a career reading specs and things like that. The protocol spec is one of the most readable and implementable things you could ever do. Like in a couple of weeks, you could easily implement a client in any language you want to around this. I think I heard that the JavaScript client came into existence over a long weekend or something. So it's not hard to bring this to new languages that do not already have. And so that answers a question back there. Like there isn't a COBOL one, but you can likely implement a COBOL one without a huge problem. And so porting this on top of legacy applications, because that would be a requirement, legacy applications don't speak RSocket, is totally a doable thing, and it's not like rewriting an entire application to do it. It's also payload agnostic. In this particular case, we basically turned an int into a string, sent the string along on the payload, parsed the int back out of the string, did something with it, turned it back into a string, sent it back across the wire, parsed it back out of a string, right? Strings are super easy to figure out what it is. I probably could have just encoded the int into the byte buff directly as 1s and 0s instead, but it doesn't really matter, right? If you're a protobuf kind of person, let's put protobufs in these payloads. If you're a JSON kind of person, let's do that. Maybe you're a large social network that has its own proprietary transport data formats. Let's do that instead, right? Something custom and binary. Well, all of these are available to RSocket. Imagine RSocket basically says, I don't care what's above me. I'm a framing protocol. The fact that you've chosen to send a given payload doesn't matter to me. I'm just transporting buckets of bits. And then also from the underside, rather than mandating that all data must be sent across HTTP2, what if we say I'm a framing protocol and I can adapt to the different transport types that you might want to use? Maybe you're in a data center. And if you're in a data center, probably your best bet these days is to use TCP. Highly efficient, has great, sort of acknowledgement, has good internal sort of buffering and backpressure and things like that. Good semantics there. But realistically, you also want to use RSocket to talk to things outside of it, right, outside of your data center. You want to be able to transfer data between the front-end web application in JavaScript and your edge router. You want to be able to transport data between your Objective-C or Swift iPhone application and your data center. Maybe you're a company that streams movies around the world and you need to transfer between, the Amazon Fire Stick stuffed in the back of somebody's television with some weird language that it's programmed in and your data center. These things are not going to allow TCP, right? Like nobody's Wi-Fi network, no cable broadband provider is going to allow just sort of raw TCP to be flying around and behaving nicely. So maybe you use HTTP1 and you use WebSockets as the underlying transport, something that opens a pipe and then we frame the data that's going across the pipe. HTTP2 is another example. The final one, Aeron UDP, is really, really interesting. If you are in finance, you have probably heard of Aeron. It's based on UDP, which is inherently unreliable, and it sort of makes it reliable, and it makes it holy crap fast, really, really fast. Makes TCP seem slow. But realistically, we see TCP data transfer rates on RSocket that are so amazingly fast that you'd really, really, really have to need to go to Aeron. So when I say flexible, what does flexible actually mean? What does it mean to use an alternative transport? Raw server. Okay, so previously we were running the raw server and it was going over TCP. This time, what if we use, see if I can remember what the class is called, WebSocket server transport. Same port. Let's just use WebSocket underneath. And the implementation just goes to like a standard interface that is the RSocket interface and how it goes down to a network transport. Here is a bag of bytes, like even the frame has been sort of abstracted and turned into a byte buffer. I want you to put this byte buffer on whatever protocol you are. If you're TCP, I want you just to send this thing over, and it's got sort of a header. It's got enough header and size information to tell the client on the other side, here is how big this message is. Maybe you're using WebSockets that have the idea of messages that are delimited in some way, that have their own sort of framing there, and so that can put it on with a little bit less information as well. We'll go ahead and fire something like this up. Nope, client's not going to work there. This time, instead of TCP client, we'll do a WebSocket client. Did I misspell it? WebSocket, there it is, socket client transport. So many WebSockets in my JVM. And this time, we're going to see exactly the same thing. Works exactly the same way. The programming model hasn't changed. You need to do a little bit of configuration issue, or a little bit of configuration difference. But one of the key takeaways from this is the realization that there is no one-size-fits-all protocol to choose for, or sorry, transport to choose for a given network protocol. There are places where TCP is really, really great if you can get it. There are places that you can't get it, and maybe you want to use HTTP2, or maybe you're Google and you've got enough routers configured in such a way that you can actually use HTTP2 successfully instead. Maybe you're in finance and you want to use Aeron because its performance is absolutely required. So having a flexible protocol, and by flexible I mean programming paradigm did not change at all. Everything you think about is an application level concern, and you configure this stuff underneath, and it happens transparently for you. So that answered the question from earlier about what transport we're using. And the answer is basically any transport and multiple transports together.
But let's say the JavaScript implementation, if the browser does not support WebSockets.
Sure.
Like does it fall back to HTTP?
So if your browser doesn't support something like WebSockets, I think you're going to have trouble with it. The WebSocket Factory that some browsers will do, so it sort of seems like it, and you can do long polling and stuff like that, may be sufficient for it to work, but I'd really have to take a look at like the JavaScript implementation to find out what that does. In fact, one of the people who worked on the JavaScript implementation is in the room and may be able to answer that question for you if he feels the need to. So let's go back to some presentation. This is probably a good time for you now. Will do. So I'm going to throw up a safe harbor statement. We're going to talk about the future a little bit. So continuing on the flexibility theme, we are, in addition to being sort of transport agnostic and language agnostic and all of those kinds of things, programming model agnosticism is actually a big goal for us as well. The RSocket interface is a serviceable programming model. You saw the code that you saw right there, but it's really designed to be a building block that other programming models can be layered on top of, right? Like you could do it, but it's probably not the best code you're going to want. And so we'll take a look at a couple more. So we've got an RPC style. So if you are sort of familiar with gRPC or something like that, I'm going to show you what an RPC style interaction over RSocket might look like. And we'll also take a look at a Spring messaging style as well. I think that's what I was going to do. Yep, alternative programming model. So this time, instead of using that raw model, what we've done is we've defined a protobuf definition. right? So this protobuf definition basically says, I have a simple service. It's going to compile into an interface. And I have a method that says request stream of values, takes in a request, and needs to stream a bunch of responses. Given a very helpful protobuf compiler plugin contributed by the Netify team, this can be turned into a set of code. So now, all of a sudden, when this goes through a protobuf compiler, it can become a simple service interface. Nope, that wasn't it. Simple service. Here we go. Generated code, never the prettiest stuff you're ever going to see. But what you take away from this is we have an interface of simple service. It returns a flux of whatever this simple response thing is for a method called RequestStream of values that takes in the incoming message and some metadata about that particular message. That's what we're seeing here. So on the server side, RPC server. On the server side, once again, we're still implementing an interface. But this interface isn't just RequestStream, right? Like RequestStream puts us in a position I talked about a little bit earlier where multiple request types that might want to request a stream would have to be disambiguated and delegated out to things. In this case, we have a method that has some kind of semantic meaning to both the client and the server, and we implement the response from this thing, right? Basically the exact same kind of configuration there. We create one of these request handling RSockets and pass in this particular server, and all of the data gets delegated to it. So we'll start up the RPC server. After fighting with it last night, I realized, you know what I should do? I should make sure these start on different ports. That way they never conflict with one another. RPC client still maintains that same kind of symmetry. So in this particular case, there is a client requesting a stream of values, sending in a message, getting something back. And so the RPC client this time goes off and runs exactly the same way that the sort of standard RSocket thing did. And so the key takeaway is this is a style, if you are sort of in an RPC kind of way of thinking, that you want to, simple service proto. If you want to come in here and you have an interaction model between your client and server that allows you to come in and say, request another stream of values, some other thing, right, that has a sort of semantic interface that it can do. And then you can, sort of generate a new proto, which may or may not happen successfully. I have no idea if I have written good code there. It may not. Oh, there we go. And now all of a sudden the server no longer compiles because we need to implement another method that has some sort of semantic meaning. This is an interesting way to do it. This is certainly the way gRPC generally works and has gained a lot of traction. I will be the first to say, as prelude to Rawson coming up here and showing you the messaging style, I don't personally like this. I think it's a bit too tightly coupled. On the other hand, I am clearly on the wrong side of history at the moment. The market is speaking that I may be incorrect in this. But because Spring is all about flexibility, we're going to give you some options.
Hello. Yes, so with the code generation that we just saw, the programming model comes a little bit higher level than what you saw with the low-level RSocket right here. And as you can imagine, implementing this isn't quite the way you would like to work with this, whereas with the code generation, you have an interface to implement, you actually get an object, and that object is getting decoded from the payload, whereas here it's a very low level. Now, the code generation, of course, solves a very important problem, which is working with multiple languages. And that's obviously, in some environments, that's going to be important. And in that case, the code generation is pretty much a solution for that. What we're thinking about is actually providing something a little bit nicer alternative if you're working in Java, because Spring is a framework for Java. What I'm going to show you, and this is a big disclaimer here, I'm not going to make the source code available. There is no repository where you're going to be able to get it. This is work in progress, just something that we're experimenting with. So the idea is just to, for for you to see that, but it's not really anything to be distributed at this time. Okay, so as Ben described it earlier, RSocket is bidirectional, and there's a multiplex connection, and when you have a connection between a client and server, once it's established, you lose the distinction between client and server. It becomes more one side can request, the other one has to respond, or vice versa. So you can have situations where a client is actually initiating requests to the server, or maybe streaming data. The server is requesting something from the client, and then the client starts streaming, say, updates about how am I doing, so the server can monitor clients, things like that. But the first thing I want to show you is the responder side from a server side. So if we have a client and a server, then what if the client, in kind of more traditional style, the client makes a request and then the server responds? What you see here is an annotation-based programming model. And that's something that we're more used to in Spring, not only from Spring MVC, but also the stomp over WebSocket support. This is the same message mapping annotation that some of you may be familiar with from the stomp over WebSocket support. And in that message mapping, we can express routing information. So while with the code generation, gRPC, you just generate a service and the routing automatically happens, here you would express some sort of routing information, and we would use the payload, information on the payload to actually determine how that routing, where that message should be handled. And as for the flexible method signature, this is quite intuitive. You can see here, this is kind of the canonical style of the interface itself, where you have a payload is given to you, and then you respond with a mono of a payload. You can do other kinds of styles, like if you wanted to inject a mono, the thing is actually available, but if you want to start composing on it, I mean, that's the idea of the flexible programming model, then you can get it in like that, so you don't have to do mono.just. If you wanted to ignore the incoming payload, you could do that as well. So you just leave out the argument. If you wanted to do, what you have to do is synchronous to begin with. It doesn't have to do any I/O. It's not, doesn't need to be. There's no waiting involved. Then there's no reason why you couldn't construct this kind of signature. Once again, this is something we support in WebFlux as well. Or perhaps you don't care to respond. So we have a mono void return value, and this last one is just a synchronous version of the same thing. Right. The other thing I wanted to show is here is another handler, and this one is going to do the same thing in RxJava. So a flexible programming model, that's another thing that it allows us to do quite easily. In fact, it sort of comes for free because we have this adapter registry that we also use in WebFlux, and that allows us to support different reactive types, including RxJava or Reactor, and you can plug others. In terms of the actual way to run this, what's here is just RSocket API code. And the actual code to send data is going to look a lot like what Ben showed with the raw API. Again, this is mostly showing the responder side, but you can sort of see what's going on here. We're going to perform, we're going to create a connection over TCP, and then we're going to perform a bunch of requests on that, and then the routing information is going to work, is going to be delegated. I'm not actually going to run this because we're running out of time, but I just wanted to show you one more thing, which is the same thing from a client-side perspective. So I shouldn't say client and server, I should say requester and responder. So if I'm on the client side, then I can also be a responder. And you will see that this actually looks very identical to what you would do on the server side, except in this case, it's the server making requests and then the client responding. And once again, we can do it in RxJava too. So most of the difference comes down to how this is hooked together. And you will see the code for that here. Make it a little bit bigger. And the other thing that I need to show is actually, in this case, we need to write a little bit of server code. And there's a handle connection method. So whenever there's a new connection being established from a server side, we're going to make these requests to the client, and then the client acts as a responder to the server. And I apologize for rushing through this a little bit, but we are running out of time. There's really a lot to cover, and this is indeed a very exciting topic. So in conclusion, I just want to point out that what we're thinking about currently in Spring and what's already available in RSocket Java is actually quite complete in terms of what you can do with it, so that nothing stops you from actually starting to use RSocket. We're looking at making this nicer to use and more familiar to Spring developers by providing an annotation-based programming model. We're going to have something for the client side as well, for the requester side, which might look like the web client, that sort of API. And then from the server side, we'll probably start with an annotation model. We might have a more functional programming model as well, but these are things that we're going to be experimenting. And if this is something that you're interested in, we'd love to hear from you and talk a little bit more about it. And you can influence the direction of this because it's still in progress. And with that, I'm going to turn over to Ben to conclude.
Yeah, so unfortunately, I'm not going to get to I'm not going to get to go through, hey, there are a million other things that the protocol actually gives you that are really, really useful. We will go quickly through those slides and pretend like they don't exist. You'll see the names, they make some sense. There's metadata and data in every single frame. We can do fragmentation that deals with MTUs and transmission sizes and things like that. Cancellation, which helps us very efficiently say, okay, I actually didn't want any of the data you sent me. Leasing that allows you to do sort of client-side load balancing. But the one I do want to talk about, because the question was asked a little bit earlier, is resumability. And there is this idea inside of the protocol, I'm not going to be able to do it justice in this short a time, that the client and server sort of keep track of where they are in the message stream as things are being sent back and forth. So that if a connection dies for some reason, the next time a connection comes back up, you can say, I was this connection that previously existed. The last frame I saw was this. The server says, okay, I recognize who you are. The last frame I saw from you was this, and each one knows to then replay whatever they have left. And sort of by default, there is no great strategy for how you store this data. It's left open to you. So you might have, for really big stuff, you might have some stuff that's really close and kept very small. In other cases, you might want to write stuff to a database because it's really critically important that it be durable against all possible failure types as well. So those are how we deal with resumability. And after this, I'm happy to talk to everybody about it. So as we said, RSocket is a bidirectional multiplex message-based binary protocol that uses reactive streams. Flexibility all over the show, but most importantly that I want you to take away from this is we have a couple of programming models that already exist. We know Spring is working on a programming model. We'd love to hear what you're interested in, what kind of styles really appeal to you, and what improvements around RSocket would make it possible for you to integrate into your application. And again, apologize for taking too long. Thank you very much for staying.